So in this video, we're going to talk about Euler's method. But before I do that, I want to go back to one of the problems that we had done on the last video. We did a slope field for the derivative of 2x, dy dx equals 2x. And we said, oh, it looks kind of like parabolas. And then when we actually found the antiderivative, because it's a basic power rule and we can do that, we said, oh, yeah, it does. It's x squared plus c. That's the family of parabolas. And one other thing that you might be asked to do is draw a curve, something through the initial and give an initial condition. And so I'm going to give us the initial condition 0, 1. And we did that on the last slope field on the past video. And what that means is you go to the point 0, 1 and you kind of go with the flow here, right? You want to go nice and smooth. You don't have to go right through all the slope fields. You just kind of want to show that your curve is getting more and more positive slopes. And this is our initial condition drawn. And I think we could guess the equation of that parabola. It's our basic parabola shifted up 1, right? So it would be x squared plus 1. Okay, so now let's go ahead then and take a peek at just a little. We'll get to differential equations is right here. It's got a derivative. I could have written it as y prime, but I got dy dx equals 2x. And we did kind of informally solve that by looking at the slope field that would be with an initial condition of 0, 1. It would be the parabola graph shifted up 1. But we can do that algebraically. Now, why do I want to do that? Because not everything's going to be this simple. So if you're ever asked to solve a differential equation, it means you want to find what y equals. Y equals what? What was the original equation? It's very seldom actually blah, but let's take a look at this. If you're asked to solve this differential equation, we're going to find the antiderivative. Right? So we think the original equation is this. And I could have put dy dx over here. I probably should have. And then if we integrate the derivative of y, we get y. If we integrate this side, we get x squared plus c. And I will just get rid of that. Okay. And now we're going to go ahead and use the initial condition. We're just going to plug it in. This says that when x is 0, y should be 1. And that tells us that the constant value is 1. So when we go back here and plug a 1 in, we get just what we thought we would probably get at the beginning of this video. Okay, so the antiderivative of dy dx is y. The antiderivative of 2x is x squared plus c. With the initial condition, we can actually solve for c. Okay, so let's get on to looking at Euler's method. Euler's method is a technique for approximating values on curves. Now, I see this isn't going to look any different. There it is. The old dy dx equals 2x is our differential equation. The initial condition is 0, 1, and we're supposed to approximate the value of y when x is 3. That's our mission here. Now, we already solved this differential equation. So we can actually find the value of y when x is 3, right? So y equals, when x is 3, we expect that y will be 10, that the point 3, 10 will be a point on this graph. Okay, Euler's method is for approximations, and we're going to use it to approximate the value when x is 3, and I'll tell you right now, we aren't getting 10, okay? But let's just look at how Euler's method works. Okay, to start with, this is not quite yet Euler's method. This is the idea behind Euler's method. Euler's method involves charts and tables, and I think if I do it this way first, you'll be able to see what those charts and tables are doing just a little bit better. Okay, so I'm just going to look at this differential equation. I'm going to do very similar to what I did with the slope fields, except slightly different. I'm not going to you can see I don't have all those points. I'm not going to draw slopes at all the points. I'm going to start at the initial condition. Boom, 0, 1. And I'm going to say to myself, what is the slope at that point? 0, 1. Well, x is 0, so it looks like the slope is 0. And I'm going to draw a line with the slope of 0 over, I guess, kind of a big interval, right? I'm just going to draw it one unit to the right and 1 unit to the left, because the slope right around here is 0, and 1 and -1 seem to be right around there, okay? Now I'm going to go to this next point I get to, where x is 1. And I'm going to say to myself, now what would the slope at this point be? So 2 times 1 is 2. So now for the next little segment, I'm going to go from here and I'm going to go up 2 over 1. And I'm going to kind of draw a line with a slope of 1 over that whole interval, right? And now we know the slope isn't 2 over that whole interval. It changes all the time, right? But I'm just going to do this for a little while. And then I'm going to go to 2, and I'm going to plug this in and say, oh, my slope should be 4. And I'm going to go up 1, 2, 3, 4, and over 1. And I'm going to draw that line segment with the slope of 4 on this little interval from 2 to 3. Do you see it's sort of starting to look like half a parabola? I mean, it's really Frankenstein together, but we're just drawing a very crude parabola using slopes over a certain interval. In this case, I'm going from 1 to 2, the same slope, 2 to 3, the same slope. Okay, let's go to the other side. Over here at -1, we would expect the slope to be -2, so I'm going to go up 2 and to the left. There we go. And over here at -2, we would expect the slope to be -4. So I'm going to go up a 1, a 2, a 3, a 4, and over 1. And like I said, we've got this very Frankenstein-looking parabola because we're using the slopes, but not at a whole bunch of points, just very crudely. And what we've done now is we can approximate the value of y at 3. And that's why we should use approximation symbols. Approximating this value, let's see, it's 1, 2, 3, 4, 5, 6, 7. It looks like we are approximating the value at 3 to be 7. Now, we know darn well it was 10. We just figured it out. But that's what Euler's method does. Now, to get a better approximation, I could have just used smaller steps. Maybe I shouldn't have made the slope 0 for a whole interval on 0 to 1. What if I just went 0 to half? And then my slope at 1/2 would be 1, and we'd start to do this curve bending sooner, and it might smooth it out a little bit. Okay, so if we have a smaller step size, a smaller interval where we keep the same slope, we'll probably get a better approximation, and it won't quite look so Frankenstein. Okay, so let's go ahead and look what Euler's does. Euler's typically sets up a chart. And so this is the same question we just did. We got 7. The same question we just did, only it's written in this format, and we're asked to use Euler's method using a step size of 1, which is what I just did. My intervals were 1. Okay, so we're going to get a point to start at. We're going to look at how much x changes, change in x. We're going to look at how much y changes, and then we're going to see if we can get to a new point. Okay, the point that we've been given is 0, 1. That's our initial condition. That's where we're starting. We've told our step size should be 1, and that's what this was, the x interval over which you drew that whole slope. So we're going to put in for change of x. Our x values are always going to change by 1. Here it was 0, 1. Here we're at 1, 1. Here we're at 2, 3, and so on. So our step size is going to be 1. Our change in x won't change. Okay, now this is the tricky part. To find delta y, I think you remember the old days. Our slope used to be change in y over change in x, and then eventually we started writing that as dy for change in y over dx. And that's what we're going to do here. I'm going to take this and solve it for dy, which basically means I'm going to multiply through by dx. And that's going to tell us our change in y. That's the one we got to calculate. That's the whole trick to Euler's. Okay? So you're given the step size and you're asked to, you're going to have to find dy. Okay, so let's give it a shot. We're going to say that dy is 2 times whatever the x value at that point is, which in this case our starting point was 0, times whatever the change in x was, which is our step. And so now we should have a new point. We started at 0, 1, and x changed by 1. So we started at 0, x changed by 1, we're over here at 1. Y, we started at 1, we changed nothing, so we end up at 1. Notice this was the 0.11. All right, initial condition 0, 1. Let's try again. I'm going to bring this point down. Our change in x won't change. It's constant. And now we're going to try this again. Our change in y is going to be 2 times whatever the x value of this new point is, times the change in x. So this is our change in y is 2. So we started at an x of 1, it changed by positive 1, so we're at now 2. We started at a y of 1, it changed by positive 2. 1 plus 2, we're now at 3. And notice that is a point we got right there. And then finally, we take this now as our starting point. X changes by 1. Calculate out the dy. It's 2 times whatever your x at that point is. 2 times your dx, which is just our 1, our change in x. And we're getting 4. We started at x of 2. It changed by 1. We're at 3. We started at a y of 3. It changed by 4. We're at 7. And you see we just approximated the value at 3. And we would say that f of 3 is approximately 7. Don't want to say equals. We want to use approximately. And that is actually exactly what we got up here. We ended up at the 0.37. Okay? Alrighty, so I wanted to just try one more with you. We'll get this on, and I'll kind of do this in little segments. So I've set up the table on this one. If you want to pause and take a minute to write that down, feel free. We are now told that our step size is 0.1, so I suspect our approximations may be a little better on this one. We have a starting point again of where x is 0. The y value is 1. Y at 0 is 1. Our step size is 0.1. And remember the trick here to get dy is we have to multiply through by dx. Don't forget the parentheses because you are multiplying this whole quantity by whatever your change in x is, and which is 0.1. So you can even write 0.1 in there for that if you'd like to so you don't forget. And then we're just going to go through step by step and find the derivative, the change in y, the x we start at, which is 0, minus the y squared, which is 1, times 1/10. And what we end up getting there is a negative 0.1. And so we can calculate out what our change in x was and our change in y was. So 0 changed by 0.1 is 0.1. We're at 1 and y went down 0.1, so we're at 0.9. We bring this new point down and we start all over again, okay? The change in y is going to now be our x, which is now 0.1, minus 0.9 squared. If you're thinking you need a calculator, you might be right. And then we're going to times by the change in x, which is 0.1. And we'll get a decimal value and figure that out. So go ahead and pause me. The answer is going to come up here in just a second. I'm going to fill in the table so that you can check your answers. Okay, so give a quick check of your table value. Check really these iterations here. A common mistake is you forget to take the old y and then subtract the change or add the change in y. So if you have like a negative 0.071 here, that's the mistake that you made. The approximation for y at 0.3 that came out to be 0.7802, which is, it's probably, I mean, we have a very small step, so hopefully it's a good approximation because, to be honest, we don't know how to find the antiderivative of this. This is not as easy as finding the antiderivative of 2x and plugging in a value, right? So we are kind of, this is really all we've got here is this Euler's method. All right, folks, thanks.